So, as promised, I did get to work on setup script for getting Google Compute Engine working, so that we're just installing under bare Google Compute Engine, not using Clouderizer, and so on. So, many thanks to Drew and Abel, and was it Sam? Yeah, Sam, who helped iron out a lot of problems. So the rest of you have a lot to be thankful for there. So we're going to both look at that, and then we're going to also look at back propagation. That is how we actually learn the weights. The weights, what else do we want to learn besides the weights? The biases, yeah, the B term, those constant terms. So, okay, so using Google Cloud Engine on the GitHub repository, the CS152, there's now a new file called Google Compute Engine Setup.md. So let's go look at that. So here's the deal. As we were working on Monday, right, I have a Mac, two of the others had a Mac, and then Abel has this Dell, which for some reason is not running Mac OS, it's running Windows. And so that turned out to, there were two big problems on Monday. One was Windows, and in particular SSHing into our machine. The other was installing the G-Cloud SDK, which is basically a command line interface to everything that's in the Google Compute platform, including all the Google Compute Engine stuff. And installing that on our Mac took us about an hour and a half, 2 hours to get that working. And there was an intricate set of instructions that we came up with on how to do that. Well, after about this problem with the Windows, and we didn't quite solve it yesterday, I found out a way to deal with all this, where we don't care about Mac, Windows, Linux, anything. We're going to just be running from the browser like a modern computer user, right? The browser is the OS. So everything we're going to do is from the browser. If you want to use a Chromebook for your work, that'll work too. So, and just a couple terminology things. So we have GCE. Whoops. And what does it stand for? Google Compute Engine, right? And this is one of the services that Google provides. In fact, several years ago, Google came out, their first product for doing cloud computing was, does anyone know what it is? App Engine. So Google App Engine basically says you will use Python, and you're going to be restricted in these various ways, but we'll give you lots of benefits to it. And then after the popularity of AWS, they said, okay, we'll just provide you raw instances. And so that's what Google Compute Engine. But this is all in top of a platform called GCP, which is, I think, the Google Cloud Platform. That's what it is. So when we go into the Google Cloud Platform console, you'll see there's a bunch of stuff having nothing to do with the Google Compute Engine, with Bigtable and with all sorts of other stuff that we are not going to care about. Okay, so, but sometimes I may say GCE, sometimes I may say GCP. That's what these are standing for. We really care more about this Google Compute Engine. Okay, so there's this command line interface that you can use to do basically everything you could do in the console. Okay, in fact, let's look at the console. So, and I can never remember, I don't want the docs, I want the console itself. Go to the console. Okay, here's where we have projects, we have billing, we have compute engine stuff and app engine stuff and other stuff. Okay, and so we're going to be interested in this compute engine stuff. But the fact is, remember the instructions before when I created an instance? I went through the UI and And it's like click here and then change this here and then click there and change this there. Sometimes it's easier if you just have like a copy and paste set of text to run a command line thing and it runs it. And that's what we're going to be doing. So we're using the gcloud command line, which will talk up to the console and do stuff via the command line rather than via the GUI. Okay? Where you run the gcloud command line from, there's lots of possibilities. One is from the Mac OS, which is fine, except it took us an hour and a half to install it, although we solved those problems. So if you want to install it on your terminal, that's fine. You could do it from Windows. The only problem is one of the gcloud commands has to do with SSH, and that doesn't work in Windows correctly. You could use Linux, and that's fine. Or, well, since we're doing cloud computing, let's do it in the cloud. But where? We can't use it on our machine because we don't have it running yet, and we need gcloud to be able to do that. So we can use the Google Cloud Shell. So what this basically provides you is from your console, you can get a shell window. And this shell window goes onto an instance that's a little baby instance, right? But it's got all the Linux stuff on it. And guess what it has installed already? gcloud. And since you're running it from the console within Google Cloud, it already has your authentication sort of set up. It'll do that stuff for you. Okay? So we're going to be using two different machines today. Machine number one is a Google Cloud Shell. So it's a shell that Google provides, and we're going to be doing our stuff there. And then eventually we'll be SSHing into our instance. Anytime we're running a gcloud command, are we running on our instance or on the Google Cloud Shell? The shell, right? If it's a gcloud command, we're running it on the shell. Okay. If it's like Jupyter, that's going to be on our instance. And a nice thing about this virtual machine is it's running, you have a persistent home directory. So if you change your vimrc or your bashrc and modify things to your heart's content, when you come back in later, it'll still be there. And it, has anyone ever used Screen or Tmux? All right, it's probably worth learning about those things. So let's say you log into a remote computer, Knuth, for example, right? You log into Knuth and you start running a command and you lose your connection. What happens when you come back and log into Knuth? What happened to that program that was running? It's gone, right? Because when your shell dies, any processes that are started from that shell die too. Tmux and Screen, they're kind of competitors, or they do the same sort of thing, give you two things. They give you an environment that can give you multiple windows. And second, multiple virtual windows. And second, you can come back and attach back to that session. So you've got a session, and it's still there and still running even when you log out. And so if you log in from another machine, you can reconnect to that session. That is what the Google Cloud Shell provides, is this Tmux thing. So if you're in the middle of VIing a file and you get disconnected and you come back in, whether it's in that browser or a different browser, it should still be there. So we're going to go to Google Cloud Console and run the Google Cloud Shell. So we're in the Google Cloud Console. And we're looking for this icon at the top right. And there it is. Tiny as can be. Activate Cloud Shell. And there it is. It gives us the tiniest little shell we can get. So let's make it bigger. And it's connecting. And away it goes. Okay. So, and it says that let's make this bigger. My my cloud platform project, maybe I haven't set up a project because I certainly didn't make a project called Nimble Pedal 21.14.017. I don't think, but this is fine. So here I am, great. And I can, do stuff. I can there, great. I want to set my default zone. So I want to be in US West 1B. The reason I want to be there is I know it has GPU instances. It's both close to us, and I know it has GPU instances. So we do that. Then we want to add a firewall rule. This is important. So when we were using Clouderizer, this wasn't necessary. Clouderizer, we just needed to enable HTTP and HTTPS. And then when we ran our Jupyter notebook, it started this other thing, right? This other virtual machine that Clouderizer was talking to. So for whatever way it was working, because when we were accessing our Jupyter notebook, it was basically via Clouderizer indirectly. Here we're going to be going directly from our machine to our instance. And we need to open up port 8888 and 8889, so because that's the one that Jupyter's using. So we're going to add this firewall rule. And it creates a firewall, and it says it already exists. Well, I already ran that. So you only have to do that one time. It's not going to hurt us. Now we're going to create an instance. This is going to be much easier than what we did before. So here, we're going to just say we want an instance. We have one accelerator of type K80, boot disk size of 30. We're going to have Ubuntu 16.04 LTS, which is part of the Ubuntu OS Cloud project. It's going to be an N1 standard 4, preemptible, and the tags equal Jupyter. That is, this instance should get the firewall rule associated with Jupyter that we just created. Okay? Because you might have tens or hundreds of different instances with different firewall rules, and these tags give you an ability to do that. If you wanted to turn on an SSD, you could add in a minus boot disk blah equals SSD. That just costs you more on a monthly, I mean, it charges you hourly, but I think it's like $8 a month on that order for the SSD. Now, I take it back. That was a static IP. I don't know what the SSD is, so I'm not going to run that. It would make things slightly quicker. So this is going to take just a little bit. Reading ahead, once it gets created, we're going to log into it. So all these gcloud commands, the first parameter of the gcloud command is what part of gcloud are you talking to? Are you talking to Kubernetes? Are you talking to App Engine? Are you talking to compute? Right? And we're talking to compute. And then within compute, we have a bunch of different parameters we can do. So in this case, instances deals with instances. You can create an instance. What else can you do? Stop an instance. Start an instance. List your instances. Delete an instance. Probably other things too, but those are the things you care about the most. Oh, and our instance was created, and we do get an IP address, which is nice, and it's running. So let's SSH in there. All right. Now, we need to keep in mind when we're SSH'd in, right, what machine we're on. And my guess is it's not quite up yet, but let's see. And if someone can figure out, yeah, where? Mine sometimes is in the top right here. Yeah. I came back this morning and it's like it was there. I don't know where it came from. So, in fact, I'm going to close this console window. So I'm going to exit from here for a moment and just leave here. I had forgotten that I already have a console window. And let's reconnect. And the nice thing about this window is it has the missing icons, including open in a new window. So I don't know what's up with that. All right, here. So what do you notice? You see the same screen, right? You see everything that was there from before, so you don't lose your context, which is nice. Okay, so we wanted to log in to CS152. Okay, we just took a short detour. We're logged in. Great. What do we want to do? I don't know. Let's read. we want to clone the 152 let's make this bigger. Okay, that should be readable. Great, we did that. And now what we want to do is run the script. For those of you there on Monday, it's great. There's only one script now. And this will take about 20 minutes. Okay? So I thought we'd all just sit and watch this for 20 minutes and just make sure it goes fine. No. We'll go ahead and go back to talking about backpropagation, and we'll come back to this. Any questions, though, before I move on? So just to give you an idea of what it's doing, and I did document the script if you want to look at it, but what it's doing is installing NVIDIA drivers, installing CUDA, which is the library for talking to the GPU, CUDA-in, which is a slightly different interface for neural networks, and then it's going ahead and installing Anaconda, and then creating an environment in that, and then installing a bunch of stuff. That's basically it. And setting up a little configuration for Jupyter so that you can actually access it from an external IP address. All right, so let's come back over, and we will return to this. So we want to be learning. The way we know we're learning, right, the way we can tell good from bad is our cost function. Cost function, by the way, is also sometimes called, anyone know a synonym? Yeah, also called a loss function. And because it's a cost function or loss function, you may sometimes see it abbreviated as C or L for loss, and sometimes J, and I'm not sure why, and that's what I'm using here. So J for, yeah, cost or loss. This is one possible loss function. Okay, it's not what we're going to actually be using, but it's just easier to look at than the more common loss function we'll actually be looking at. And as far as how you train a network, there's no real difference here on this cost. One thing we have learned is that your loss function can include a regularization, right? So the regularization, if you remember, looked like we have plus some lambda times the sum of our weights or the sum of our weights squared or something like that. Something that is taking into account the fact that having a lot of large weights is not so good. So what are we doing here? We're basically taking the average. Okay, let's just read this from inside out. What is this? Y to the paren I. The expected value of what? Yeah, not the ith layer. The layers we're using brackets. This is the ith input example. And this is the target of that input example, right? It's what we want, the desired value. Y hat at I is the prediction. So if Y is equal to Y hat, the loss for this training example is going to be 0. Right. Now, why do we have the vertical bars here? What's that? Yeah, it's an L2 norm. So, but why do we have an L2 norm? Is it L? Because it's a vector. Exactly. I mean, it depends. If we're doing binary classifications, it's a vector of size 1, right? It's just a value we could look at, subtract, square. But since it's a vector, we want to look at that length of the vector, basically. Okay? So, in fact, looking at one specific example here, right, if we look at y of I, that equals a vector be kind of yi1, yi2, dot, dot, dot. And y hat at I has a similar look, right? So this is basically saying for the first neuron in the output layer, here's what gets predicted. Okay, so basically what we're going to do for this norm is we're going to take the summation of y I j, let's say, minus y hat I j squared, and the square root of all that. Let me erase some of this to make it easier to read. And then we square that again. So basically, what this is equal to is just the sum of the square differences. And again, the superscript is which training instance we're looking at, and the subscript is the number of that neuron in the last layer. So our overall cost is the average of the costs for each of the instances. They're always non-negative, right? And we talked a little bit on Monday about when we're going to be looking at this loss, and in particular, when we're going to be updating our weights. At one extreme is we use our entire batch, okay, and our entire epoch. So we look at every single training example, we calculate what the cost is for each one, we average them up, and then we'll use that to drive back into the network and update the weights.
Sorry,
Drew.
The subscript is the ith example. What is, sorry, the superscript is the ith example. What is the subscript?
The subscript is over the output neurons. Because the subscript is always the which neuron it is in that particular layer. Okay? So, and again, in the simplest case where we have one neuron, it becomes very simple. Right? Just take the difference between what you have and what you want, square it. If we're taking the average across all of our data, then we're going to get a very good idea of how to update our weights such that we end up with a better cost function. We could, on the other hand, just go through and every time we do a calculation for a single instance, look and see, well, what is the cost for that? And then try and update our weights based on that. And that'd be very jerky. So what we normally do is mini batches, right, where we'll break up our full epoch into small batches, large enough to fit in the GPU. And we'll basically say this is a random sample of all the instances, and so this will give us an estimate of the true cost. All right. As a review for forward propagation, right, we have our weights again. We stacked all of our transposed weights, right? So this was, so W of L means the weights for layer L. And it consisted of the weights for neuron 1 at layer L, right? And this is basically a bunch of values, right? Because it's actually transposed. So it's a bunch of values across here, and then we have W2, L, transpose, and all the way down. So the number of rows represents what? Say it again. The number of rows is the number of neurons, right? So this is number of neurons. And the number of columns? The number of, yes, the number, which we can also just say is the number of neurons in the previous layer, right? Okay. A is in fact the activations from the previous layer. So when we multiply by A, so let's actually just look at what's A look like. So how many columns in A? Yes, one column. And how many rows? Yeah, so it's the number of neurons in layer L minus 1. Okay. So basically we multiply that together, we get a weighted sum, we add on B, and we still get a weighted sum, and what it looks like then is something like this, right? So this is the one column. At the end of Monday, I talked about vectorizing this for multiple instances at the same time. I'm only looking at doing one instance right now. Okay. And one thing you should note, some presentations of neural networks don't have a B term, that bias factor, explicitly. They have an implicit bias factor by saying that there's always a fake neuron that's always outputting an activation of 1. And so the weight that you give that is basically a bias term. Okay. We have an explicit bias term, but it can, in some cases, make that slightly simpler to look at if you think about it that way. Okay, and then for A, we just take G, which is our activation function for this particular layer, and apply it to our weighted input. Okay. So questions on that? Okay. And that, of course, has the same size as Z does. All right, and we want to just define something. So the Hadamard product of two same-sized matrices is just the element-wise multiplication. So we'll call this, let's say, O dot as our representation of that, or I guess it could be target. Yeah, anyway, so does that make sense? We're going to be using that to simplify some of our formulae. All right, before we go on, let me provide some motivation. So we've got ourselves a neural network. And we have, let's say, an output or multiple outputs. And let's look at, I don't know, this particular neuron here. Okay? And here's what we're interested. So we're, you're familiar with Maxwell's Demon? Yes? No? Does that ring a bell? So Maxwell's Demon, it was this idea that Maxwell had that you can imagine, if you will, a fish tank with a plexiglass middle in it, okay? And a small, tiny, tiny, tiny little door in it that can be open and closed, okay? Imagine some little demon in there that can open and close that door at will. And they're going to look at, I guess this would be molecules coming in, atoms, let's say, coming in, and fast ones, it's going to open the door. What it's trying to do is segregate the fast-moving stuff from the slow-moving stuff. So it's basically anti-entropy. So it'll take some warm liquid, and it'll separate it out, so you have hot liquid over here and cold liquid over here. And all it's got to do is just control whether the fast-moving particles go through onto the fast side, and the slow-moving goes through on the other. And it just goes and it looks and it sees, oh, it's a fast one. I want to open a door to let it go into from the slow side, so I want to go ahead and open the door. Or there's a slow one coming to the fast one. And there's no such thing as free lunch, right? You can't do that. And it's because the demon would take energy in order to do it. But anyway, Maxwell's Demon. This is our demon. So this is our CS152 demon. And the CS152 demon is sitting there, and it wants to look at making the cost better. Okay? So we have our J, where J, let's just say for a particular instance, is a function of our weights and our biases. And I guess X and Y, right, our input. But in some ways, X and Y are fixed here. The only thing we can really change is W and B to adjust the cost. And the demon says, you've got a particular cost now. I'm in charge of this neuron. What could I do to the weighted input to change the cost? Okay. So what's the value of this weighted input? If this is the dth neuron in layer L. All right, what's our syntax for that? So how do we represent the weighted input? So Z, because it's the weighted input. Subscript D, because it's the dth neuron at L. Okay? And we'll assume we're just looking at a particular instance. So this is our output right now. And the demon says, what if I just increase it a little bit? Okay? So instead of Z sub D at L, I'm going to go Z sub D at L plus delta Z D at L. Okay? Just move it a small amount. How does that affect the cost? Is there a path sort of from here all the way out to the cost function? Yeah, in fact, there's probably a lot of paths, right? Because this outputs an activation that goes to all of the next layer. So those are all affected, or could be affected, assuming there's a non-zero weight. And then those are all affected, and those are all unaffected, and so on. But we have a way of representing the rate at which J changes based on how this neuron changes. Okay? Because J is a function of other things, but as well it's a function of Z sub D at L. So if we look at the partial derivative of J with respect to z dl. That tells us how sensitive j is when there's a change in z, right? So what would it mean if this were 0? Can the daemon do anything to affect the cost? No. And what's a very large number? Yeah, the daemon can make a big change there, right? So what we want to look at is what's the value of j when, let's see how I want to describe this. Let's look at delta j. What's delta j equal to, right? So because we made this change, well, that's going to basically be the partial derivative of j with respect to z times how much did we change z, right? Which we already defined as delta z d at L. So that's how much z changes. The daemon is just, everything else stays constant. Only thing we're looking at is the one daemon assigned to that one particular weight. Okay? Does that make sense?
This z term takes into account the w, the b, and the x, right?
The z term here takes into account the incoming a, right, from the previous layer, plus the weight and the bias. That's how we got the weighted input. But you can even think of it as, I don't even care. I'm in charge of this, and I'm going to just arbitrarily change the input, because I just want to make that cost function better. Later on, we'll see what would happen farther upstream, how we would affect those.
Where do you get the delta from?
The delta here,
Yeah, just like add it.
this is the daemon. The daemon says, I am allowed to make a small change, right, to and this is because we're using calculus and we want sort of infinitesimals. We can't do big things. So I'm allowed to make a small change to the weighted input. I'm going to make this amount, delta, right? Just delta z. That's how much it is. We'll look at how it chooses this in just a moment. But let's say the weighted input is 152, and the daemon says, okay, what happens if I add 0.1? So instead of 152, it does 152.1. Right? So this is the daemon thinking to himself. And will that make the cost higher or lower? So they change, the daemon changes z from 152 to 152.1 is the cost function. We don't know what the original cost function is. It's some non-negative value. Does it go up or down? Well, here's our formula for it, right? The change is the partial derivative times the delta. What's the delta? 0.1. What's the partial derivative? Give me some ranges. Could be, we talked about what happens if it's 0. The daemon can do all the tweaking it wants, nothing's going to change. How about, like, could be negative or it could be positive? If it's positive and we change delta by 0.01, what happens to the cost? It increases. If it's negative, what happens? It decreases. So what should the daemon do if it knows the derivative? Right, let's say it can move it by 0.01. That's all it's allowed to move it. Should move it up or down? It should what? Well, if this is negative, it should move it up. And if this is positive, it should move it down. Or another way to think of it is we want delta j to be positive, negative. We'd like this to be negative. So we don't get a control over the partial derivative. But if the partial derivative is negative, we want our delta to be positive and vice versa. So we want the two signs to be different. So we want the signs to differ. So here and here, in order to decrease the cost. If we're an evil demon, then we would want to match, right? Does that make sense? So we are going to use this partial derivative as a measure of error at a particular neuron. And then we're going to actually use it to adjust weights and biases so that our z's will go up and down appropriately. Does that make sense?
Is that just the derivative delta j with respect to that neuron? Or like
So this delta j is how much does j change, right? What's the change we made? So there's a before and after. The before picture is we had a bunch of weights and biases, right? The after picture is everything was the same except this neuron now outputs 152.01 instead of 152.
why do you multiply it?
Here? Well, so what I'm saying is if I make a small change, let's look at a different example. So let's say we have y equals x squared, right? And now I want to say, so x is equal to 3. And I want to say, and so y is equal to 9. What happens if delta x equals 0.1, right? That is, if I try and evaluate this at 3.1 rather than 3.0. One way is I can go through and reevaluate everything, right? That's what we could have done here. We could have said well, if we increase this to 152.1, let's go calculate everything and we can figure it out, right, what the change is. But we don't want to do that. We want to use calculus. So how much does x squared change if x increases it by 0.1 when x is 3? That's the same thing as saying I'm going to call it f of x, right? What is f prime of x? Sorry, what's f prime of 3? Isn't that roughly the same thing? So what's the slope at 3 for this function? And what is it? It's 6, right? And so therefore, if we increase x by 0.1, we would expect x squared to increase by 0.6. Right? Now, obviously, this doesn't work if you have large deltas, right? If you say delta x is 100, then we do not expect 103 squared to be 9 plus 600. Right? But for small amounts, this works. And that's part of why we have this learning rate, because we're going to be dealing with small amounts. So that's the same idea we have here. This is, so we take, to make it clear, delta f is going to equal f prime of 3 times delta x. That is exactly equivalent to delta j equals the partial derivative of j with respect to zd, right? So this is dy dx, right? Times the amount we change it. And as long as this is a small amount, then this is a approximation, you know, a reasonable approximation.
So is the amount determined by the learning rate that we give it?
The amount is going to be determined by the learning rate, yes.
So it's kind of constant for every one that you
Yes. Yes. So the first thing we're going to do is we're going to accumulate all these errors for all of our instances. So we're going to actually figure out what is the error for here. So I'm going to show you in a moment. Once we get the error for z, that's going to allow us to eventually get to the errors for w's and b's. And we can get then the associated errors for w's and b's. So we can say if we change this weight by this amount, this small delta, how much would the cost change? We will average those across all of our mini batch. So we'll have a error for every weight and bias for the first instance, the second instance, the third instance, the fourth instance, all of them in our mini batch. We'll average them together, and that'll tell us our average error, and then we'll use that to go update. And basically all we'll do is we'll just say, take the old weight, add or subtract the error appropriately. It's really what we're going to times the learning rate. Questions? So what do we need? Well, we need to know how to compute the error. Give you a hint here. This is called back propagation. All it really is a large application of the chain rule. Okay? But it has a fancy, fancy name. Developed in the early 80s. So we are going to forward propagate in order to compute what y hat is. And then we back propagate from the cost, or the error, back all the way through, applying to all the weights and biases and z's and a's to figure out what the error for each of those is. Okay, so that's the back propagation. So at the last layer, we are going to define, right, that's what the triangle equals is, so we're going to define sigma at, and I'm using capital L as the last layer. So we're saying that the error at the last layer is defined to be the partial derivative of j with respect to the weighted input at the last layer. And sigma L is really a vector because we've got a bunch of errors, right? We've got the error for the first neuron, the error for the second neuron, the error for the third neuron, and so on. Okay. But it's easier to just talk about the entire set of errors. So we have defined sigma L, but we're going to need to figure out how to compute it. We need to figure out, given that we know what the error is at layer L, we want to compute the error at layer L minus 1. Okay, and I used in here, and we'd really be better off talking about L because L sounds like layers. So lowercase l, lowercase l. So we want to calculate sigma at L minus 1, give it sigma at L. Does that make sense, right? So basically, we're going to go to the output neurons first, and we're going to say, what's the error here? And it seems like that should be easier because we're really close to the cost function there. And then once we've calculated that, how can we go back a step and calculate the errors at the next layer, and the next layer, and the next layer, all the way back? Can we go back all the way to the input? Well, the input was given to us. We don't get to change the input, right? Unless we're looking at things like are you familiar with this, like the stylized images? Like here's a picture, and I want to do that picture looking like this Van Gogh, Starry Night. So there, you could actually go and change the input. Here's the happy face I gave you, right? And now I want you to make that look like Van Gogh, right? So this is the, and we have a style image here. So the way this works is basically you take your input and then you adjust it, just like you would adjust weights, but you actually go all the way back to actually adjusting the input so that it's reducing our cost function, where our cost function is measuring how close are we to the original image and how close is the style of this image to the style of the given image. So it is possible to go back to the input, but for what we're looking at now, we're not going back to the input. Right? We're going back all the way to those very first weights and no farther because our x is fixed and our y is fixed. All right, what else do we need to be able to compute the error of? What are we going to be changing? Do we actually update weighted inputs as a part of our learning? We don't change weighted in, we can't change weighted inputs because there's no daemon in there that gets to fudge the input. It has to follow the formula. So where's the weighted input come from? What? The activation function is after the weighted input, right? It's applied to the weighted input. Where does the weighted input come from? The previous layer and weights and biases. So the weights and the biases are the things we're needing to change, so that's what we need to know. We need to know what the error for a given bias is so that we can then go update that bias. So that's going to be partial derivative of j with respect to a particular beat, given that we already have the error for that layer. So once we know the error for that layer, how can we find the error for a particular bias? And similarly, how can we find the error for a particular weight given the error for that layer? So let's just look at here. So this is the partial derivative of j with respect to w sub I super L. So that means what? The ith neuron in layer L. And what the heck is the j here? And maybe this isn't great syntax, but what's that? It's not the example that uses the parens. This W, oh, I can write over here. Oh, that looks cool. So Wi at L has what form? What's it look like? It's not a number. It's a vector, right? So we got a vector of kind of W1, W2, all the way to W, whatever, K, right? Because we've got to wait for every incoming activation. So this just says the jth one. So this is the ith neuron at this layer. That's the weight of the one that's hooked up to the jth neuron of the previous layer. So I is this layer. And J is the neuron in the previous layer. Right, so we're looking at a specific weight. We've got to hook up from here, and this is the number J, to here, which is number I, and this is a layer L minus 1, and this is layer L, and we've got one weight between those, right? And I'm going to just write it on the line instead of writing it below. So this is weight L I J. Okay. So the partial derivative of the cost with respect to a single weight given the error for there. So we're going to figure out how to do these. And these all mostly apply from just following the chain rule. But can you see once we get these, how we'll then be able to update the weight? Right? We know what the change will be. We know whether we want to increase or decrease the weight in order to affect it. And we're going to average these over a bunch of instances. So one instance may want this weight decreased, but most of the other instances want it increased by a lot. It's going to increase. The one that wants it decreased will make it increase not quite as much. Right? And that increase will cause our cost function to go down. So if the weight wants to increase, what does it say about the partial derivative of that weight? Positive or negative? Negative, because we're trying to increase the weight in order to decrease the cost. Okay? So let's look at the last layer. All right, so again, this was defined, actually. The sigma sub j at L is defined to be the partial derivative of the cost with respect to a particular weighted input. And then let's just use the chain rule to break this apart. So we're going to say we're looking at I'm sorry. Let's Back up a second. Right now we're not deriving it. Right now I'm going to give it to you, and we'll derive it a little bit later. So this is how we calculate it. We take the partial derivative of, this is the chain rule. The partial derivative of j with respect to the activation, because if we look at this, j is equal to something, 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 plus we've got our activation is our y hat, right? So we've got j equals some g of z, right? So we're going to say we've got our j over here. We've got our output neuron here. Our j gets calculated by summing up. And we've got on the left side the z, and on the right side the a, right, where a equals g of z. And so if we want the partial derivative of j with respect to z, we can just take the partial derivative of j with respect to a times g prime of z. Okay? And that's what we're doing here. And the superscript L is just, again, because activation functions may change based on the layer. Yeah. All right. So if we want to take so j is some function of a, and a is some function of z. Yes? So j is f of g of z. We can talk about the partial derivative of j with respect to z. And that we're doing here, right? The partial derivative of j with respect to z. How do we do that using the chain rule? We say dj dz equals, right, ignoring partials for now, equals dj d a times dA dz. dA dz is g of z, g prime of z, right? And dj dA is this partial derivative of j with respect to a. Okay. And so let's look at how we calculate each of those. Is it easy to calculate this? Assuming g is differentiable, then we're okay. Let's talk about it right now. So let's say g of x equals sigma of x. Sorry, not a very good sigma. Sigma of x, okay? The sigmoid function. 1 over 1 plus e to the minus x. What's g prime of x equal? Well, that equals, let me see if I get this right. I think it's g of x times 1 minus g of x. The derivation is a little bit of algebra that's not all that fun. But we may have to do it just to verify. So let's look. So g prime of x. Let's see, we have 1 over y. So the derivative of that is negative 1 over y squared. Is that right? So we have negative 1 over 1 plus e to the minus x. And then times the derivative of e to the minus x, right? Which is e to the minus x times the derivative of negative x, which is negative 1. So we get e to the negative x over 1 plus e to the negative x. Okay, we'll throw squared in here just to match what we said it should be. Does that look good with that change? Okay, so this equals e to the negative x over 1 plus e to the negative x squared. And that equals, we're going to add and subtract 1. Okay? So we have a 1 plus e to the x and then a minus 1. And so we're going to pull apart this one. So we're going to have 1 over 1 plus e to the negative x plus negative 1 over 1 plus e to the negative x squared. That brought me some of the way I wanted to go, but not all the way. Let's see. All right, let me
Sigmoid of x times
1 minus sigmoid of x. Yeah.
You can take that
Oh.
1 plus e to the x common. You can take that. So, 1 over
So from here,
So, no, last step.
from here, yes.
You can take 1 over 1 plus e to the negative
Oh,
x common.
and make this, yes. So this equals
1 over 1 of
g of x
g of x times 1 minus
plus minus g squared of x, right? Equals, yes, g. I don't know what's happening, sorry. Okay, let me. All right, so we've lost all the rest of our context. What we have is sigma prime of x equals sigma of x times 1 minus sigma of x. And that is this g here, right? Assuming that we're using a sigmoid activation function. All right, let's look at the next layer. So at layer L minus 1 given layer L. So what the heck? This is the error. At layer L, right? And these are the weights of L. So we're basically going to be doing a weighted sum of those, right? And then we're going to do an element-wise multiply times the derivative of this previous layer times the weighted inputs of the previous layer. So let's think about that. So basically, this is the weighted error, right? So we've got an error at a given layer, and we need to know, okay, what's the error at the previous layer? Well, if there are a lot of high weights between here and here, then our error is going to be bigger, right? Because we're magnifying oh, that sounds crazy. Okay, right, so layer L minus 1, layer L. We've got these, let's say, a particular weight here. And if we have an error here, what happens to the error here? Should this one be bigger or smaller than this one? Let's say W is equal to 32. Okay, and we've got an error of 1 here. 2, let's say. So delta equals 2. What's this delta equal? It's equal 64. Does that conceptually make sense, right? If I'm a demon here, and I'm looking at my weighted input, and if I increase it, it increases, so increases my cost. That is, my delta is 2, right? If I increase my weighted input here, my cost is going to increase 2 times as much. If I go to this previous layer, what happens when I move the weight a little bit? Is it going to be more or less than the amount here? It's going to be more by a factor of 32, right? Because whatever I do here changes this value by 32 times as much, which means then it's going to change the entire amount by 64 as much. If, on the other hand, W is small, let's say 0.5, then we're going to have half the error here that we did here. Okay? But we also, of course, have to take into account, that's assuming that the derivative here is 1, because we have the effect of the derivative as well. Because of the fact that as we make a change here, we're applying the activation function. So we have to take into account, okay, yes, we have a weight of 32 difference here, but when we look at the error here, we've got to first apply the derivative of the activation function, and then multiply that by the weight times the error at the next layer for a given neuron. I actually am going to stop now because I just wanted to show you the rest of the setup. Okay? So we will come back to this on Monday. So we were over here, and it finished the install at 1836, which is probably about a half an hour ago. All right, it says log out. Okay, we will log out. And then it says stop your instance. And the reason we want to stop the instance, basically we need to reboot to get our drivers installed. Okay, so it's going to stop. So that's what we have to do our one-time setup. That was it. Okay. Now what do we do? How do we start our instance? Well, we use gcloud start. It's got to finish stopping first. There was probably a command to restart it. I just didn't know what it is. Let me move this up so you can see it better. So that's done. We'll start it. That's great. So when we created the instance, it told us its IP address. But the IP address can change. It's ephemeral. So we need to find out what its IP address is because we want to be talking to the Jupyter server. So once it starts up, we're going to go find out what its IP address is. While it's doing that, it's worth knowing that There are some terminal preferences. I don't know if you can see this on copy settings. So you can copy just when you do a select, it'll copy for you, or you can do Control X, Control V. That's going to be relevant in a moment. All right, so here's our external IP address. See it? We want to save that, and it just saved it. Because I selected it, saved it. Okay? So we have the external IP address, and now we're going to go back and it's in my clipboard and I don't want to lose it. I'll put it right there. Did you see, by the way, how long it took to restart? Right, stopping was quick, but starting was quick too. It took 30 seconds, 45 seconds, so much better than the Clouderizer. All right, and we have a prompt here, CS152. How many of you used environments in Python? Like Conda or virtualenv, something like that. So we're using that here. Conda is a sort of package manager and virtual environment. The idea is you can have one environment set up with this version of Python and this version of TensorFlow and this version of XYZ library, and a totally other environment with all sorts of other different settings. So we have an environment set up for CS152. Everything's installed in there. Jupyter's installed in there. Python's installed in there. Everything. But you have to run a special command to activate an environment. I put that in your bash RC already. So you're already in that environment, and that's why it tells it to you right here. So when we run Jupyter, we're running the Jupyter from this environment. We say Jupyter Lab, and we're not done yet. Because, as it says here, you're going to see a line that says to log in with a token. So here's the deal. We've got, right now, a wide open Jupyter server running on that IP address. Do we want anyone to be able to go in and use our GPU? No. We want only us to be able to do it. So we have a secret. And that secret is the token right here. So anyone who comes in with that secret can go ahead and access. So we're going to go back over here. We're going to paste it in here. The problem is that the host name it gives is not very good. CS152 or 127.0.0.1, which is localhost. Right? Neither of those are going to work. We need that IP address that we carefully copied before, which is right here. So we'll copy that IP address. We'll replace the host name. What's that? You still have to have the 888. Yeah, that's the port number. That's the one we opened up in the firewall. And that's just the standard Jupyter port number. When you run Jupyter Lab, you can choose another port number, but that's fine. OK, here we are. We are running. Let's run lesson 1. Are we running with a GPU? We better be. We will check and make sure, but we better be. And I don't know why with this install, first off, I don't know why it's not finished yet. There you go. We do get one warning when we're importing the FastAI imports. Yes, it says true, true, good. We have all of our examples. We have a cat. And then here's our, you'll find this also runs probably quicker. Well, yeah, it has, so this is just downloading the weights. And that's, Google has good pipes, right, to the outside world. So the weights come down quickly. This takes a little bit of time. Yeah.
Question on the submission. Will I create a separate branch locally once we pull from your master?
So here's the deal. You're going to have 2 Git repositories. You have the CS152 repository that we'll be using throughout the course that you'll be having to do Git pulls every so often. It's unlikely you're going to be making changes to that. And then for each assignment, you'll have a repository. So when you went on to GitHub for Education. It made a repository for you, right? And that's the one that you're going to be submitting with. There's no starting Python notebook for your submittal. You're creating a notebook from scratch, right? To the best that you can, try not to copy and paste, but to actually remember and figure out what it is that you need to do in order to do the learn, fit, and so on. That will help. Okay, so it's still running. But this is, what is it doing right now? It's doing the data augmentation, right? It's making these zoomed and other stuff. So when it gets to actually learning, you are going to be impressed. And this would be a little quicker if we were running an SSD, right? Because it's reading and writing a disk, reading and writing a disk. And let me look at the instructions and see if there's anything else you do. To kill Jupyter Lab, I'll show that in a moment. You just Control C, and it's going to say, are you sure you want to kill Jupyter Lab, and hit Y. And to stop your instance, use stop. Remember to stop your instances so you don't get charged, right? I've already paid like $8.50 this month in charges. I had not realized I was using my personal account, which doesn't have the credit. So yeah, that's a lot of money. No, just $8.50. So. All right, let's just finish watching this because it'll be very satisfying. I will be in my office until 3 today. If you want help with setting any of this stuff up, I'm happy to. Yeah, it's actually a lot quicker with the SSD. This is interesting.